Testing.
Mm.
More minutes. Right. See. Okay. Who else showed up? Let's see. And the other Kaylee. Let's see. Allison, Madison, and Michael. Where could they be? Let's see. Yep. Before we get started, when I introduced this material Tuesday, I had a Chapter 9 crossword puzzle that didn't look right. So I went back and reworked it, and I've replaced it. It looks like this. I've replaced it in the in Brightspace. So if you got one of the old versions, this one should have a comment here saying spell out any numbers. The reason I say spell out the numbers, so if it's 3, THRE, because the crossword puzzle program that I'm using doesn't allow for numerics, only alphas. Okay. So today what I'm going to try to do is get through review for Exam 7, Chapter 9. And we're not rushed. I've got 29 problems. Maybe we can get through all of them. If we can't, then we'll be able to pick the rest of them up next Tuesday for the exam that's on the following Thursday. And then that will allow for Tuesday, the 6th of May and the 8th of May will then be open for will then be open for final exam review. Okay, so let's see how many we can get done today. This is version 2, the review documents, and let's see. Okay, it's going to be difficult to get everything on there at once. The following molecules contain, which of the following molecules contain central atom with sp2 hybridization? Remember, sp2 hybridization is if carbon has one s orbital, and actually we're talking about two s's and two p's, then a 2p hybrid only requires these three to go into 3 sp2 hybrids. So if we look at it that way, then we know that from our VSEPR model that 3 groups is trigonal planar. So what we want to look for is a molecule that has only 3 groups around the central atom. If we look at the first one, we see that aluminum has 4, phosphorus has 4. If we look at the B, we find that boron has 3. So that boron trifluoride is an excellent candidate. If we look at C, we find that we have 3 bonds and 1 lone pair. That's 4. That's sp3 hybridization. That won't work. And if we look at D, most nitrogens have 4 groups, and E only has 2. Well, beryllium has 2. So technically that would be an sp hybrid. So the best answer here is B, without a doubt. All right, we'll go to number 3 next. Consider this molecule and the following hybridization choices. What's the hybridization of the carbon atom that's double bonded to oxygen? Okay, we've got 1, 2, 3, 4 carbons. All right, the one on the end is triple bonded to nitrogen. That's chlorine and hydrogen. And then we've got a carbonyl group. That's what we call it in organic chemistry. There we go. There's our molecule. Okay, so the hybridization for the carbon that's double bonded to oxygen is this one right here. We don't have any lone pairs. We've got 2, 4, 6, 8. There's already an octet around that carbon, and carbon can't exceed the octet. So this is 3 groups is sp2. While we're here, this is sp3, right? 4 groups there. sp3, 4 groups there. And this carbon has sp hybridization. Only 2 groups. Okay, so the best answer to that one is B. Let's see. Oh, what's the hybridization on the nitrogen atom? Okay. What's missing from that nitrogen? 2, 4, 6. That nitrogen has a lone pair, right? It's got 2 sp hybrid. I mean, that one wasn't marked, but I thought I'd take advantage of it. Let's see, who just dinged in? Allison. Okay. All right. That was number 3 and number 4, actually. Number 5. Let's see, we have 1, 2, 3, 4, 5 carbons. And we have a triple nitrogen on the end. I'm gonna put that lone pair out there anyhow. This one has, now the way we, when you see an organic molecule written this way, actually it's written this way to emphasize the fact that any hydrogens are bound only to the carbon that they're next to. So these 2 hydrogens here are like that. Then we have another carbon here with a double bond oxygen. And then we have a hydrogen here, the double bond there, and 2 hydrogens here. So that's 1, 2, 3, 4. This is 2, 4, 6, 8, 2, 4, 6, 8. Okay, so we got all our octets together. What's the hybridization on each of the carbon atoms? So these are those labels, those 1 through 5 are just labels for the carbon. So 1, 2, 3, 4, and 5. So we're looking at this one has 1, 2, 3 groups. That's sp2. This one has 3, sp2. That one has 3, sp2. That one has 4, sp3. This one has 2, sp. And it only specified the carbons. We've already done that nitrogen. We know it's sp. So the best one here is, let's see, 2, 2, 2, 3, and 1. 2, 2, 2, 3, and 1. That's A. Remember, when the easiest way to tell what your hybridization is look at how many groups are around the carbon or the atom, the central atom, and count up the number of groups, and then just start counting them up. If there's 1, 2, 3, 4 groups, right? That's as far as we can go with P's. Then if you have 5, you put a D out there, and if you have 6, you have 2 Ds. So it's really simple, actually. All right. Okay. I'm still missing Madison and Michael. All right, next. Number 6. What's the hybridization of selenium in selenium hexafluoride? Okay. I'm going to do this the long way. So selenium has 6 valence electrons. Fluorine has 7 times 6 is 42. That's equal to 48 total. So selenium goes in the middle, and we have 1, 2, 3, 4, 5, 6 fluorines. 2, 4, 6, 8, 10, 12. 36. 2, 4, 6. We have 6 to make an octet around fluorine. We have 6 more of our available electrons, and we have 6 fluorines. So that uses all of those up. Okay, there's our molecule. Okay, what is the electronic and the molecular? There's Michael. So if we have 6 groups, this is octahedral. All right. There's 1 plus 3 is 4 plus 2 is 6. This is D2sp3 hybrid. Let me see. Do I want to tackle one that's not highlighted? Yeah, let's do 8 while we're here. No, it's not highlighted, but it does offer an opportunity to deduce from this skeleton what is our Lewis structure. And then how many of its atoms are sp hybridized? Okay, so we have to assume that this skeleton is all the elements, all the atoms that are in the molecule. We don't have anything else in that molecule but what we see here. Okay. Tetracyanoethylene. All right. If you knew what that name meant, you could fill this model out just like that. But we're going to have to do it the long way because naming conventions for this type of molecule have not been worked out yet. We haven't done that. This is organic chemistry, but we can do it. The Lewis structure will tell us. If we have 1, 2, 3, 4, 5, 6 carbons, that's 4. That's 24 electrons, and we have 1, 2, 3, 4 times 5 valence electrons for nitrogen is 20. So we have 44 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so that's 26 electrons. Okay. Now, if we follow the convention for Lewis structures, we'll work from the outside in. Right. If we put 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now we have 2 electrons left. Where are they going to go? Well, we're trying to make an octet. So if we put those 2 electrons on any one of these, then it's going to be difficult to make an octet for all of them. One thing to recognize here is this molecule is symmetrical. In other words, whatever we do to one, we do to the other 3. So rather than put the 2 electrons here, they should go right there. That way, we can take 2 pair here and make a triple bond. we can take 2 pair here and do the same thing for each one. Like that. Then, with only 3 here and 3 there, we can take these 2 and make a double bond. And that gives an octet here, here, here. Everybody's got an octet. Okay? So how many of the atoms have sp hybridization? Well, there are 2 here. That's 1, 2, 3, 4. All these carbons are sps with 2 groups. And these have sps. So 4 more. So we have 8 with sp hybridization. And that's wrong. How many of the atoms are sp hybridized? Only 2? Maybe what we wanted there was sp2 hybridized. sp2 hybridized, yes, would be these 2. So that's a mistake. Maybe that's why I didn't highlight this one, because I needed to correct that mistake. If we, I'll tell you what, let me edit this. sp2 hybridized will be, now that's correct. Right? But if it's sp hybridized, you're going to have 8 sp hybridized. That one and that one times 4.
Hey, Professor Bly.
Yes, sir.
In our review document that has the answers, you have 8 atoms on it. So you were right with the 8.
Oh. Okay, I'll tell you what. I made the wrong correction. I should do this like that and change this one here to E. Oh, no, D, excuse me. D. There we go. Now my key is correct. All right, moving on. To number 9. A pi bond is the result of what? Remember when we have, what example should we take? Say, carbon dioxide. Right there. And we would have a double bond here, double bond there, 2 lone pairs. So how did we form that pi bond? And there's 1 sigma on either side. Well, with 3 groups on this side, we have sp2 hybrid, and with 2 groups on this side, we have sp hybrid. What that leaves us with is an unused p orbital on this side and unused p orbital on that side. And for carbon, we have 2 unused p orbitals. So one of those sets of p's overlaps with these p's to give you the pi bond. And the other pi orbitals overlap with these p's to give you the other pi bond. So what we're doing is we're overlapping unused p orbitals, which would be D, sideways overlap of 2 parallel p orbitals. That will give you a pi bond. Okay. Did we lose somebody? I heard some ding-a-lings there. Michael Aker. No. We just haven't seen Madison, I think. Yeah. Madison's the only one missing now. Okay, number 10. Use the molecules below to answer the next 3 questions. All right, at the end of our lecture, 2 days ago, we talked about this molecule, which was benzene, right? But if we convert this bond into a single, we get the next molecule. Yeah. Just so that I'm drawing it the same way they are. And then if we take away another one, make it a single bond, then we get this molecule. Right? So the reason they write C6H6 is each one of these carbons has a hydrogen on it. In organic chemistry, we just leave the hydrogens off, but that way it won't get too busy. But we understand that anything that's not written is a hydrogen. And anywhere you have two lines coming together is a carbon. Right? So that's why the formula is C6H6. So for this one, we would have a hydrogen here. We would have a hydrogen there, one there, one there, and two hydrogens here. Right? So this would be C6H8. Yep. And similarly here, we would have one hydrogen there and there. And then we would have two at each one of these locations. And that would be C6H10. Okay. So that being said, what's the question? Which molecules have p orbitals that share an electron pair to create pi bonding? Which molecules? Well, all of them do. Right? This one has nominally three pi bonds. That one has a pi, that one has a pi there, and this one has one pi. So to answer the question, all of them have pi bonds. The difference is these are isolated pi bonds, except these would be conjugated. And this one would not be conjugated. So this would have a delocalization of electrons in that system. That one wouldn't delocalize at all. And this one would form a delocalization for the entire molecule, which makes it very, very stable. So nominally, those are pi bonds, but those pi electrons form a delocalized, say, donut, so to speak, around that molecule. That's why benzene is extremely stable. Okay. Moving on. Oh, we got the same thing over again. What are we talking about here? Which molecules have equivalent carbon-carbon bonds throughout the molecule? Okay. Equivalent bonds throughout the molecule. That's only this one, because they're delocalized around the entire molecule, and all bond lengths are exactly the same. Now for this one, that bond length, this bond length, and that bond length, they will all be the same also because they're conjugated. But these will be different bond lengths. They'll be longer, which puts strain on the molecule. And this molecule is even further strained. But to answer the question, benzene is the only one that has equivalent carbon-carbon bonds throughout the whole molecule. All right, looks like we got some molecular orbital shorthand here. And if you've been practicing your molecular orbitals, this won't be a surprise to you. If you haven't, then this is going to be complete Greek, which is sad. So the electronic configuration for a particular diatomic species is given. What's the bond order for the species? Well, that's a simple calculation, right? Bond order equals the bonding electrons, right? Number of bonding electrons minus number of anti-bonding electrons divided by 2. So all we have to do is look for the asterisks and the non-asterisks. The non-asterisks are bonding. So sigma 2s has 2 electrons. Sigma 2p has 2 more. Pi 2p, which means there are 2 pi's in there with 2 each, which is 4. So we got 2 plus 2 plus 4 is 8 bonding electrons. Anti-bonding, we have a sigma star 2s with 2, and we have a pi star 2p with 2. So that's 4 divided by 2, which is equal to 4 divided by 2 is 2. Okay, so your bonding order for this molecular system is 2. Right. Number 13. As the bond order of a bond increases, the bond energy does what and the bond length does what? Okay. As the bond order increases, what does that mean? It means that the bond is getting stronger. Right? It's like the difference between single, double, and triple bonds. Only with the bond order, you can have fractions. But still, as the bond order increases, you get an increase in bond energy. Right? What happens to the bond length? Well, as you increase the bond energy, you decrease the bond length as the nuclei get closer together. So you strengthen the bond and you decrease the bond length. So increase, decrease, which would be C. All right, number 15. How many unpaired electrons in the F2 2 plus? F2 2 plus ion are based on molecular orbital theory. How many unpaired electrons? The order of the molecular orbitals are this. Okay, so you're given the template for the molecular orbitals there. So we have sigma, let's see. Yeah, sigma 2s, sigma star 2s, sigma 2p, pi 2p, yes. Then pi star 2p and sigma star 2p. Okay. So how many electrons are we dealing with here? Well, fluorine has 7 valence electrons. Notice we're starting with 2. We're leaving out the 1s. So we're only interested in valence electrons. Valence electrons for fluorine would be 7 each. So 2 times 7 equals 14 electrons. But we lost 2 of them to make that ion. So we only have 12 electrons. Now we can use the Aufbau principle and fill from lowest to highest energy. So sigmas have 2. Pi's have 4. So that's 2, 4, 6, 10, and then 2 more. And we don't even need the last one. Okay. So the question was, how many unpaired electrons? These are going to be paired, right? Sigma only has one bond, and those are all paired. Right? There and there. These two for that pi, these two for that pi. This is 1, 2, 3, 4, and this is 1, 2. So we have two unpaired electrons in the molecular orbital, let's see, structure, the molecular orbital structure for F2 2-. All right. Let's see about 19. Let's see, am I going to need hybridization of central? Okay, no. We're going back to the valence bond theory. Hybridization of the central atom of ClF2 plus. What this tells me is that chlorine is in the middle. Right? Chlorine is below fluorine, so it's less electronegative. It has more metallic character, so it goes in the center with fluorine and fluorine. And hybridization. Okay, so how many valence electrons are we talking about here? Well, we've got 7 here. We've got 14 here, minus 1 for that charge. So this is 20 electrons. Okay, we've already used 4 of them. So now we have 2, 4, 6, 8, 10, 12. That's 4 electrons. We have 2 here and 2 here. And we have to do that. If we don't put that plus there, then we're saying that this is not an ion. And we have to account for all the electrons in a neutral molecule, but it's not neutral. It's a cation. Okay, now the question was, what's the hybridization of the central atom Cl of this atom right here? Well, 4 groups is sp3, right? sp3. Okay, 21. Which of the following does not contain at least one pi bond? All right. C, D, and E. What are we dealing with here? H2CO. H2CO, that's formaldehyde. Carbon dioxide. C2H4, which is ethylene. And C2H6, which is ethane. And none of these are. So again, we're looking for not contain at least one pi. Not at least one pi. Okay. So let's see, we have 2 for hydrogen, 4 for carbon, 6 for oxygen. So that's 12 electrons. We know what this one is. We've drawn carbon dioxide so many times. Right. That one's not the candidate. It's got 2 bi-bonds there. C2H4. All right, so we have 2 times 4 is 8, plus 4 is 12 electrons. This has 2 more, which is 14 electrons. All right, so the structure for CO2, we've drawn that one. How about H2CO. We have C, O, and then H's. And that uses up 2, 4, 6. So we have 6 electrons left, 2, 4, 6. Okay. We want to make a double bond here because we can't do it on that side. So we do that. Right. There's a pi bond. Right. So this is not it. This is not it. This is C2H4. So 2 carbons and then 4 hydrogens. Right? 2, 4, 6, 8, 10. So that leaves us with 2 electrons. Right? To make an octet, we take those 2 and make a double bond. There's a pi bond. Right? That's not it. And C2H6 would also put that. These are hydrogens. Okay. 2, 4, 6, 8, 10, 12, 14. Use them all up. This one has no pi bonds. That's your answer. All right, 24. Feel like we lost somebody. Let's see. Still got Michael, Alan, Kaylee. Right, Allison, Kaylee, and Allison. Okay. Still looking for Madison. Madison's not here. Okay, 24. Complete the Lewis structure for the following molecule. So this molecule gives us the starting point with just single bonds. All right, so we're going to have, and the way we draw this, remember, the hydrogens are attached to the carbon that they're sitting next to. So this carbon has 3 hydrogens. And then it's attached to the next carbon, not to the hydrogen as shown, but to the carbon. And then that hydrogen, and above it is another methyl group. Like that. Okay. Then we go to this carbon, which has an oxygen here, and this carbon, and that nitrogen. Okay. All right. So let's count up all the valence electrons first. And we have 1, 2, 3, 4, 5, 6, 7. 7 hydrogens. We have 1, 2, 3, 4, 5 carbons. So 5 times 4 is 20. And we have 1 oxygen, which is 6. And we have 1 nitrogen, which is 5. So that should be, let's see, 10, 12, 18, 38 electrons. Okay, now we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 electrons. So it's 12 electrons left over. Work from the outside in. These are all filled. They have their octets. So we're actually working from this side. 2, 4, 6, 8, 10, and 12. Then we make our octets. Right? How do we make an octet here? Well, the best way to make an octet here is to take those 2 and those 2 and make bonds out of them. So there's a triple bond. This one already has 3, so we only need 1 bond here with 2 lone pairs. So that oxygen has 2 lone pairs, that nitrogen has 1 lone pair, and the rest are octets and duets. And now the molecule has how many sigmas and how many pi's? Anywhere there's a bond, any kind of bond, there's a sigma. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigma bonds. And anywhere there's a double or triple, you can count pi's. So that's 1 pi. And this is 2 pi's. So there are 3 pi bonds, 13 and 3. That's E. 26. Consider the skeleton structure shown below. Draw the Lewis structure and answer the following. Okay, this is another case where everything that's in the molecule is given right there. There's nothing that's assumed. These are all the atoms that are in that molecule. Okay, so if we add up, let's see, 2 5s and 2 4s, we have 18. 2 4 6 means we have 12 electrons left over. 2 4 6 8 10 12. Okay, used them all up. Now we got to make our octets. So how do we make an octet out of this one? Well, let's see. How about we do this? Now we could make a triple on this side, right? And that would give that an octet, but it wouldn't give an octet over here. So in order to make an octet on the other side, we have to make another triple bond. There. And that will give us both the octets, and it will probably give us the minimal formal charge. Right? If we calculated formal charge, oxygen starts out with 4, nitrogen starts out with 5, and we have 1, 2, 3, 4 minus 4 is 0. That's 0. Formal charge. And then 1, 2, 3, 4, 5 minus 5 equals 0. Right? So that's ideal. All formal charges are zeros. That's good. Okay, so the answer, how many pi bonds does this molecule contain? It has a pi here, a pi here, a pi here, and a pi here. It has 4 pi bonds. 27. Which of the following molecules contains the shortest carbon-carbon bond? All right. Okay, B and D. B and D for E. Okay, we got C2H2, C2H4, and C2H6, and C2Cl4. C2Cl4, correct? Yep. Yeah, that's right. Okay, we did these two before, right? This one is a single bond there, and then 3 here with hydrogens. Drawing on the work we did in that previous problem. This one, on the other hand, has like that. A double bond between the carbons. This one, we lost 2 more hydrogens. This one is acetylene. Okay. Just draw it out and satisfy yourself. You'll come up with triple bond. So single, double, triple here. But this one is like that one right there. Only it has a carbon, carbon, and it has chlorine here, chlorine, chlorine, and chlorine with a double bond. Okay, Now, we're looking at the shortest bond or the strongest bond. It means the same thing. If we were only looking at these three, the shortest bond would be the triple, right? If we didn't have that one to go on, then we'd have to break a tie between this one and this one because they're both double bonds. If that's the case, if I'm sneaky and I change the question and put something else up there that's just doesn't fit, and you're comparing this one and this one, then you have to look at what's happening to the molecule that would possibly weaken that bond. What would weaken this bond? Well, chlorine is more electronegative than hydrogen. It's pulling electrons that direction, right? So it weakens this bond. And a weakened bond is a longer bond. So if we compare these hydrogens versus chlorines, this is going to be a stronger bond. Okay? But as written, the answer is A. All right, 28. Let's see. Still got time. When comparing diberyllium and dihydrogen, let's see, we've got 4 statements. And I suppose we're looking at which of these are true. That's what I deduce from the answers. Okay. So we're comparing this one and this one. We know this one's going to be like that. We know beryllium, diberyllium, it's going to be like that. Now let's look at the answers. Okay. The answers tell us that we're talking about molecular orbitals. All right. So this is only going to be a sigma from 1s with 2 electrons. There we go. 2, 4, 6, 8. Now the bond order makes sense. 4 minus 4 divided by 2 is, excuse me. Yeah, is 0. We don't predict a diberyllium. Here we go. Okay, so hydrogen has a higher bond order. Yes, that's true. 1 versus 0. How about 3? H2 is more stable because it only contains sigma 1s electrons. Well, that's another way of saying 2. It has a bond order because it only has 2 electrons in the 1s and no anti-bonding electrons. Yeah, so technically 3 is also true. And 4, H2 is more stable because it is, no. Diamagnetic and paramagnetic had nothing to do with stability. They are only expressions of the molecular orbitals paired versus unpaired electrons. So C is the only one that makes sense. It's got 2 and 3 are true. After a long time of my messing around. All right, back to 29. Which of the following species is paramagnetic? So what's the difference between paramagnetic and diamagnetic? Para is the Greek prefix that means alongside of or with, which means that the molecule is drawn into the magnetic field. Dia prefix is opposite to, is opposed to. So these molecules are not drawn into the magnetic field. And if you pour liquid oxygen into that horseshoe magnet, it'll stay there until it evaporates. If you pour liquid nitrogen in there, it goes right on through, doesn't stop. So this is an example of diamagnetic, and this is an example of paramagnetic. Okay, which of the following species is paramagnetic? Well, we got oxygen already, right? How about carbon? Is carbon paramagnetic? Well, carbon is going to have 4 C2 would be 8 valence electrons. So we would have sigma 2s sigma star 2s sigma 2p, and it's to the left. So next one is pi. Excuse me. No, it'd be pi first. It'll be pi 2p and sigma 2p. So 8 electrons would be 2, 4, and 4. So these are all, right? These are all paired. So carbon would be diamagnetic. How about fluorine? Difluorine. So it would be sigma 2s, using only the valences. Sigma star 2s. This would be sigma 2p, pi 2p, then pi star 2p, and sigma star 2p. So these fluorines would have 7, 14. 2, 4, 6, and 4 is 10, and then 4 more. So fluorine is also diamagnetic. Those are all paired electrons. And then lithium, let's see, lithium. If it's even possible, lithium would be sp mixing. So we would have sigma 2s sigma star 2s pi 2p sigma 2p. Then we would have pi star 2p if we need it. So how many valence electrons do we have in lithium? We have 2, right? No, 4. No, it's yeah, it's 2. 2 valence electrons, right? So we'd have just 2 there, right? This one would be diamagnetic or paired, right? So the only paramagnetic in this whole bunch is oxygen. Let's see how we're doing on time. 10 minutes. Okay. 30. Okay. Let me check my roster here. No new ones. All right. 30. For how many of the following does the bond order decrease if you add one electron to the neutral molecule? Okay, so we need B2, C2, P2, and F2. Let's do it like this. B2, C2, P2, and F2. All right. So how many valence electrons are we going to have here? We're going to have 6 here. 6 electrons. There's 3 plus 3. Carbon's going to be 8 valence electrons. Phosphorus is going to be not same as nitrogen, 10 valence electrons, and fluorine is going to be 14 valence electrons. Okay. There's no mixing with this one. There's mixing for the rest of them. Yeah. Okay, so the no mixing, fluorine is in the second group, so we're gonna leave out the core electrons, and we're gonna go sigma 2s, sigma star 2s. We're gonna do 2p. Right, no mixing. Pi 2p. Then we're going to do pi star 2p and sigma star 2p. So we have 2 here, 2 here, 2 here, 4 there. So that's 6, that's 10, and 4 more here. All right, so that's all we need. And what was the question? Oh, how many of the following does the bond order decrease if you add one electron? Okay, so what's the bond order for this one? It's 2, 4, 8. 8 minus 2, 6. Divided by 2 equals 1 bond order. All right. If we add one electron, where is it going? It's going into that one. So now we have 8 minus 7, which make this one 1/2. So that one does decrease. All right, so this one decreases bond order by adding an electron. Okay. Let's see. Let's go to boron. So boron would be sigma 2s, sigma star 2s, and then this is mixing, so we're going to have pi. Pi 2p and sigma 2p, and then pi star 2p and sigma star 2p. Okay. Carbon is also mixing, so it's going to use the same template. Phosphorus is the same as nitrogen, which has mixing, but now we're into the third period. And this is going to be sigma 3s, sigma star 3s. With mixing, we have pi 3p, sigma 3p, pi star 3p, and sigma star 3p. Okay. So we have 6 electrons here. We have 2, 4, and 6. So if we add an electron to this one, where's it going? It's going into a bonding order. This would increase bond order. Okay. Carbon is 8, so it would have 2, 2, and 4, and then 2 more, and then 2 more. This would be 2, 4, 8. And if we add 1 more, it's going into a bonding order. This would increase the bond order. And 10 for this one is 2, 4, 8, 10. So if we put one in this one, it would go into an anti-bonding order, and this would decrease its bond order. So we have two that would decrease their bond order by adding one electron, simply because the added electron goes into an anti-bonding order, orbital, molecular orbital. Okay, we got 5 minutes. Let's see, how many more do I have to go? No. Not count them. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we are going to have to. Let me see if this is a good place to break. 30, 32. Order the following from the shortest to the longest bond. Okay. Let's go ahead and do 32 and then we'll stop there. Because I may be able to use some of this for 32 and save some work writing it up. Okay, do we have boron? Yeah, we have boron here. We have carbon, yes. Hydrogen. I need hydrogen. I don't need phosphorus. And nitrogen. So we need dinitrogen, which is mixing. So this would have to be reversed. Pi and sigma. Like that. For nitrogen. Now nitrogen has, let's see, 10 electrons. Okay, we got these done. The one I'm missing is hydrogen, which is 2 electrons. This was easy. 1s2. So how do we answer this question? We go for bond order, because bond order tells us the strength of the bond and the length of the bond. The stronger the bond, or the higher the bond order, the shorter the bond. And then we'll have to maybe augment it a little bit, but let's do this first. So the bond order for, let's do the bond order on this side. 32, isn't it? Yep. So what's the bond order here? Well, 6 would be back to here, right? 2, 4, 6. So we would have 4 minus 2. 4 minus 2 divided by 2 equals 1. Okay. This one is 8. So we would have 2, 8, which would be 6 minus 2. 6 minus 2 divided by 2 equals 2. This is bond order. Okay. This bond order is 1. All right, 2 divided by 2 is 1. Nitrogen, we've done that one before, but we'll calculate it again. This is 2, 4 there. Let's see. It's 8, 2 more here. So we have 4, 5, 6, 7, 8 minus 2. 8 minus 2 divided by 2 equals 3. Okay. So when we're talking about the shortest, longest bond, the highest bond order is nitrogen. Okay. The problem is, look at what orbitals are contributing to that. We're getting out here into 2s. So those nuclei cannot get close to each other. I mean, it's definitely a strong bond, but you still got a core of sigma 1s and sigma star 1s inside that. So those nuclei can't get close to each other. Whereas the hydrogen atoms, they've only got the one proton and they've got the one electron, and they can get very close. So actually what we're looking at is this is the closest one. And if we're going to put them in order, right? If we're going to put them in order, this one is the shortest. Right? That's the shortest. Then the next one is nitrogen, because the rest of them are in the second period. So now we can put them in order. Since they're second period, we can put them in order by their bond order. So nitrogen, and then carbon, and then boron. So HNCB. HNCB is A. All right, that was the one trick, is to recognize that this is first period. Right? Very, very close. Even though it's a single bond, we're still talking about very close atomic nuclei. All right, so we're going to pick up on Tuesday with 34. Let me make myself a note here.